This is the first lecture of Tengren Zhang from NUS about convex RP2 structures on surfaces.
Okay, so thank you all for coming. And before I start, I would like to thank the organizers for this workshop, for inviting me to give this mini course. It's my second time in ICTS. It's always a pleasure to be here. Okay, so a month ago, Mahan told me to give this mini course on convex RP2 structures on surfaces. He just assigned me the problem. Okay, so I'm going to stick to my mandate and just stay with convex RP2 structures on surfaces. Okay, so let me begin by giving you a brief introduction, a very, very brief introduction on my plan for this series of 3 lectures. Okay, so I'm going to let S be an orientable finite type surface right, with negative Euler characteristic. Okay, so what does this mean? So orientable finite type surface means that this guy is of genus G with n points removed. Okay, and the n points that are removed, we call them punctures of the surface. Okay, so the picture you should have maybe something like this. Okay, you have a genus 2 surface with a bunch of points, finite number of points removed, okay? And the fact that I require this S to be of negative Euler characteristic means that 2g minus 2 plus n has to be positive, okay? So when the genus is 0, you need to have at least 3 punctures. When the genus is 1, you need at least 1 puncture, and when the genus is bigger than 2 or bigger, you don't need any punctures, okay? Okay, and then we want to so the object that we're interested in, so object of interest, right, is this space which I'm going to denote by C of S F V. Okay, so this is the deformation space of convex RP2 structures on S, okay, with finite volume. Okay, and one of my main goals today is to explain to you what are these convex RP2 structures and what does it mean for them to have finite volume. Okay, so my plan here, aside from the goal that I just stated, lecture 1, I would like to describe to you the topology, right, and the symplectic structure. On this space. Okay, and then the second lecture, I would like to describe this structure on this moduli space, the topology and symplectic structure, in a more explicit way. So I'm going to give you double coordinates. Right, on this space. Okay, so what do I mean by double coordinates here? Well, here I have a symplectic form, okay? So this means that you can find coordinate functions, x1 to xn and y1 to yn, okay, so that your symplectic form omega can be written as the sum from I equals to 1 to n of dxi wedge dyi. Okay, so this is as explicit as you can get in terms of describing a symplectic structure and the topology. Okay, and then the third lecture, I'm going to talk about the relationship between cubic differentials and the convex projective structures with finite volume. And if I still have some time, I'm also going to talk about the augmented deformation space of CS of finite volume. Okay, so let me just say that this part here, right, is mainly the work. I'm going to use the work of course, it's Bill Goldman and Ludovic Maki. Okay, and also some stuff from Fort Gontroff, Bonahon Dreyer, right? And also some recent work between Sunja, Anna, Vinhad, and me. Okay, and this stuff here, right, in lecture 3, okay, this here I'm going to use the work of Labourie, Loftin, and also Benoit and Hulan. Okay, so this is roughly what I'm going to cover in the lectures. Okay, so let's get to our plan today. Okay, so we want to describe what is CS of FV. Okay. Now, before we even talk about convex projective surfaces, okay, let me recall some basic facts about RP2. Okay, just to make sure that everyone's on the same page. Okay. So first, what is RP2? Okay, RP2 is the set of lines. You can think of this as a set of lines in R3 through the origin. Okay, and you can also, okay, and this is naturally also you can think of it as the set of vectors in R3 that are non-zero. Okay, consider up to scaling. So I quotient out by the multiplicative group of R. Okay, it's because every line in R3 you can choose any vector in there, and the projective class of that vector gives you that line. Okay, so this also tells you how to put the topology on RP2. Right? You take the standard topology on R3, you take the subspace topology on R3 minus 0, and then you take the quotient topology here. Okay, but for us, RP2 is more than just a topological space. Okay, RP2 has geometry. Okay, that we will be using, and we're going to follow Klein to describe the geometry on a space, right, by its symmetry group, okay? And so in the case of RP2, the natural symmetry group we're going to use is PGL3R, right, which is the set of 3 by 3 invertible matrix with real coefficients. Consider up to scaling again, okay? Now the GL3R action, GL3R acts naturally on R3. Okay, and so when you take this quotient by R, the multiplicative group of R, this gives you a natural action on RP2. Okay, so this guy acts on RP2, and this action is in fact transitive. Okay, and so this RP2 equipped with this symmetry group, right, is what we call the projective structure on RP2. Okay, and the guys in here we call them projective transformations. Okay, the group of projective transformations on RP2. Now, inside of RP2, there are certain subsets that are preserved by projective transformations as well. Okay, and one important such subset is called a projective line. So a projective line in RP2, okay, is the projectivization of a plane in R3 through the origin. Okay, so you take a plane in R3 through the origin, and then you look at all the lines through the origin that lies inside of this plane. Okay, this gives you a subset of RP2, and we call that subset a projective line. Okay, that's a one-dimensional subset inside of RP2. Okay, then now if you can also think of RP2 dual. Okay, so what is this? This is defined to be the set of linear functionals on R3, right, linear maps from R3 to R, so R3 dual, with the zero linear functional removed, and I consider these things, again, up to scaling. Okay, so this RP2 dual, and this guy is naturally in bijection with the set of projective lines in RP2. Right? And what you do, you just take any projective class of linear maps here, and you just assign to it the kernel. It's kernel. Okay? So this is a very natural identification, and so for the rest of my 3 talks, I will no longer distinguish between this set and this set. Okay? I will think of this as the same thing for the rest of my in-course. Okay, so these are the basic stuff we need. Now, to talk about convex projective surfaces, I first need to tell you what are properly convex domains. in RP2. Okay, and some related structure there. Okay, so definition. An open set, omega inside of RP2, okay, is properly convex. Okay, if the following two conditions hold. Okay, first, the closure of omega inside of RP2 lies in an affine chart. Of RP2. Okay, and what is an affine chart of RP2? Well, as I said, it is just the complement of a projective line inside of RP2. So when you take RP2 and you remove a projective line, what you get is something left that is homomorphic to R2. Okay, but our affine chart again is not just a topological space; it has some geometry there. Okay, and the natural geometry is affine geometry. Namely, if you take the set of projective transformations that leaves this open set invariant. Okay, and you look at, so that gives this, so you have this open set equipped with the automorphisms of the open set, so which is a subgroup of PGL3 that leaves invariant. That turns out to be isomorphic as a geometry to affine group acting on affine space. Okay, so we call this an affine, that's why we call this an affine chart of RP2. Okay, and the second condition here is that this properly convex, this domain is actually convex, meaning if you take any pair of points, PQ inside of omega, okay, there exists a projective line segment in omega between them. Okay, so what is a projective line segment? It's a connected subset of a projective line. Okay, so what are examples? So if you think of the board as my chosen affine chart for RP2, then your properly convex domain looks something like this. Okay, so this is omega. Okay, its closure lies inside of the chart. And if you pick any pair of points, PQ in here, okay, there's a projective line segment inside of them, between them. Okay, another example is maybe you don't need your domain to be C1. Okay, you can have a polygon. Okay, this is another example of a properly convex domain. Okay, or you can have something that has a line segment in the boundary, okay, but it's C1 as well. Okay, so this is also okay. Okay, so what is not okay? What is not a properly convex domain? So all of RP2, right, that's not okay because it doesn't satisfy the first condition. Okay, or if you take RP2 with a projective line removed, that's also not okay, right? Because if you take the closure of this guy, this is all of RP2. Right, so it doesn't lie in an affine chart. And to violate convexity, you have something like this, right? This is also not okay. Okay, because if you take a point P here and the point Q here, there is no projective line segment that lies inside of this domain. Okay, so these are properly convex domains. Now here's a fact. Okay, so if your properly convex domain omega is an ellipse, and it's an ellipse in this affine chart. Right, so an ellipse is something that's preserved under affine transformations. Okay, so it makes sense to talk about an ellipse in the affine chart. Okay, then, okay, the automorphism group of omega. So what is this? This is the subgroup of PGL3R. Okay, so maybe I just define. So this guy here is defined to be the set of G in PGL3R that takes omega back to itself. Okay, the automorphism group of omega turns out to be PGL2R. Okay, and it's not any PGL2R, it's a PGL2R sitting inside of PGL3R irreducibly. Okay, meaning that this subgroup here doesn't preserve any projective line inside of PGL3R. Okay, it doesn't preserve any projective line, doesn't fix any point. Okay, and there's a unique one such thing up to conjugation inside of PGL3R. Okay, and in fact, right, if you think of this omega together with its automorphism group as a geometry. Right? I specify a topological space together with a group of symmetries. Okay, this is isomorphic as symmetries, right, to the Poincare disk equipped with the Poincare metric and the isometries of the Poincare disk. Okay? So, and this isomorphism here takes projective line segments to geodesic segments here. Okay? So one way you can think about what this fact is saying is that the studying convex projective domain, properly convex projective domains in RP2 is a generalization of studying isometry on the Poincare disks. Okay? Also, this tells you that, in fact, when you start with this properly convex domain, right, which is an ellipse, okay, then there is a natural Riemannian metric you can define on this, right? Basically, you just pull back the Riemannian metric on the Poincare disk onto here. Okay? And this is called the Klein model for the Poincare disk. Okay, so the natural question is to ask, well, if I have a more general properly convex domain, okay, is there a natural metric I can impose, I can put on that domain that is invariant under the automorphism group and kind of generalizes what happens in this case? Okay, and the answer is yes. And the metric you can construct this way is called the Hilbert metric. Okay, which is what we're going to talk about next. Okay, so to define the Hilbert metric, we first need to talk about this well-known projective invariant called the cross ratio. Okay, so what is it? So let A, B, C, D be 4 points in a projective line in RP2. Okay, so that no 3 of them agree. Okay, so you can have A equals to B, C equals to D, that's fine. You cannot have A, B, C being all equal. Okay? Then you can define the cross ratio, C of A, B, C, D, okay, to be A minus C times B minus D divided by A minus D times B minus C. Okay, where here, where for any PQ in ABCD, okay, P minus Q is the Euclidean distance between PQ, right, in some affine chart. Containing ABCD. Okay, so let me draw a picture, maybe illustrate what's going on. Okay, so you have these 4 points that lie inside of a projective line, okay, and these are 4 points, so you can definitely choose an affine chart that contains all of them. Okay, so in the affine chart, I'm drawing them like this. Okay, and then you just choose a Euclidean metric on this affine chart, meaning a Riemannian metric, so that it's invariant under translations and rotations. Okay, and then you just measure the distance between these points in that metric, and then you just take this ratio, this product and ratio. Okay, so it turns out that this quantity is well defined, meaning it doesn't actually depend on the affine chart you choose or the Euclidean metric. And it's a projective invariant, meaning that you take these 4 points and you hit it by a projective transformation. Then you get 4 new points that still lie in a projective line. So you can measure the cross ratio of the new 4 points, right? And that will give you the same answer as the cross ratio of the original 4 points you started off with. Okay, so this is the cross ratio. And then using this, you can define the Hilbert metric on a properly convex domain. Okay, so for any PQ, okay, maybe I should say, so let omega be a properly convex domain. Be properly convex. Okay, then for any PQ inside of omega, okay, you can define the distance in omega between PQ, right, to be the logarithm of the cross ratio of A, B, PQ. Okay, and what are these points A, B? Well, you have your convex domain here, omega, and then you have a point P and a point Q here. What you do is you draw the projective line through P and Q. Okay, if P equals to Q, you just take any line through that point. And then this line is going to hit the boundary at two places, okay? I'm going to call this point A and this point B. Okay, and here you just take the cross ratio of these 4 points. Okay? And you take the logarithm. So, yeah, you need to, so there's something here I'm skipping, which is that if you take this cross ratio, right, and you evaluate it on a quadruple of this in this order, this number is at least 1. Okay, so when you take the logarithm, this is at least 0. And in fact, it's going to be 1 if and only if P equals to Q. Okay? Okay, and some facts. Okay, these are also not so hard to verify. First is that d omega is a proper path metric. Okay, so it's a metric, meaning it's positive, definite, and satisfy the triangle inequality. Okay, and it's proper, meaning that bounded and bounded closed sets in omega with respect to this metric is compact. And this being a path metric means that for any pair of points in omega, you can find a rectifiable path between them in this metric, whose length is equal to the distance between the 2 points. Okay? And second, this metric d omega is invariant under the automorphisms of omega. Okay, and this is a consequence of the projective invariance of the cross ratio. Okay, and finally, okay, so here for this I need to put a half here. Okay, this d omega is the hyperbolic metric. Right, when omega is an ellipse. Okay, so this is a generalization of what you saw in that fact over there. Okay, and then associated to this Hilbert metric, right? There's a natural notion of volume as well. Okay, I'm going to give you kind of a useless definition here. So the Boltzmann volume, or the let's call it the Boltzmann volume. Yeah, so my convention, you do PQ, and then A is the first, A is the one closer to Q, and B is the one closer to P, okay? Yeah, you have to make it in this order in order to make sure it's bigger than 1, okay? What about what is an ellipse? So an ellipse is the zero set of a quadratic form. So, okay, another way you can think of it is you just take your plane, you take the circle, okay, and then any affine transformation of the circle, okay, that will be an ellipse. So you might not preserve, you might take the axis and make some shorter, make some longer. That's fine, okay. Okay, so now the Boltzmann volume on the Boltzmann area, we'll call it volume, right, is the two-dimensional Hausdorff measure. Of the Hilbert metric. Okay, so this is a volume on omega. Okay, so this definition here is not very enlightening. In fact, you can actually write down what this Boltzmann volume is quite explicitly. Okay, because I didn't say it here, but this Hilbert metric is a Finsler metric. Okay, so it is not Riemannian in general. Namely, it's not infinitesimally given by an inner product, but it is infinitesimally given by a norm. Okay, and using that, you can actually write down an infinitesimal formula for the Boltzmann volume as well. Okay, but I'm not gonna do that here because I really don't need for this mini course. And later on, I'll tell you a different way to think about what it means for a surface to have finite Boltzmann area. Okay. Okay, so with this, we can now talk about convex projective surfaces. Convex RP2 surfaces. Okay, so definition. A convex RP2 surface is, okay, I'm usually going to use sigma to denote my convex RP2 surface, is something of the form omega quotient out by gamma, right, where omega inside of RP2 is a properly convex domain. Okay, and gamma is a group of projective transformations that act properly discontinuously and freely on omega. Okay, so if you don't have this free condition, then this guy here has a structure of orbifold. You might have some singular points. Okay, so to make it a surface, I just impose this freeness condition. Okay, so, okay, and then I say that, so this is a convex RP2 surface. Okay, and I say that two convex RP2 surfaces, sigma 1 equals to omega 1 quotient out by gamma 1, and sigma 2 equals to omega 2 quotient out by gamma 2 are projectively equivalent Okay, so this is the natural notion of when two such surfaces are isomorphic. Okay, are projectively equivalent if there exists a homeomorphism F from sigma 1 to sigma 2. Okay, so that when you lift it, this F to the universal cover. Okay, when you lift it like this, okay, this guy here is the restriction of a projective transformation on RP2. Okay, so this will ensure that not only are these two things homeomorphic, the project structure on them is preserved as well. Okay? Okay, so what's next? No, there's no, I mean, there's no notion of identity yet, right? There's no marking. It's just yeah, okay. Well, that's a good point. We're going to do that very soon. Okay, so okay, yeah. So maybe let me just state two facts that are maybe kind of obvious but important to know, important to notice. And the first is that gamma here is actually the fundamental group of your convex RP2 surface. Okay, it acts as deck transformations on omega, which I can think of as the universal cover. Okay, and second, because of the projective invariance of the Hilbert metric and the Boltzmann volume, both of these descend to metrics and volumes on the quotient surface. Okay, so the Hilbert metric and a Boltzmann volume descend to omega quotient by gamma. Okay, so whenever you have a convex projective surface, it comes naturally with this metric and volume. Okay. Okay. So in the case when the convex RP2 surface is compact, okay, there's actually a very, very nice theory that has been developed. Largely, okay, so it came from Benzakery and Kuiper and people from long ago, but I think it was famously generalized to all dimensions by Yves Benoit, okay, where he viewed it from the point of view as properly convex domain on which you have a co-compact and proper group action, okay? But because in this mini course we are going to not focus on compact surfaces, or not always focus on compact surfaces, okay, I'm not going to talk about that theorem very much, okay, but I thought I should just mention it because it's really a big part of this story that I'm just avoiding, okay? But for our purposes, to analyze convex projective structures on convex projective surfaces that are not compact, okay, an important tool, right, is this theorem due to Ludovic Marquis, okay, where he characterized the possible holonom, the possible conjugacy classes of elements that show up in gamma. Okay, so it says the following: that sigma equals to omega quotient by gamma be a finite type convex RP2 surface with negative Euler characteristic. Okay, then every non-identity element in gamma, okay, is conjugate to one of the following. Okay, so the first possibility is gamma is conjugate to something that's diagonal, right, where all the three eigenvalues are distinct and of the same sign. So I can assume that lambda 1 is larger than lambda 2, which is larger than lambda 3, which is larger than 0. Okay, and we call these things, this type of elements, hyperbolic. Okay, and then the second type of thing that you can be are these things called quasi-hyperbolic elements. So in this case, your eigenvalues need not all be distinct. Okay, but if the two of them agree, then you must put a 1 here. Okay, and here lambda 1 is not equals to lambda 2, and they are both bigger than 0. Okay, so these are called quasi-hyperbolic. Okay, and the last possibility is when all the eigenvalues are the same. Okay, so you can pretend that it's conjugate to this guy. Okay, so when I write square bracket, I mean this is a projective class of matrices. Okay, inside of PGL3R. Okay, so these are called parabolic elements. Okay, so let me make two observations here. First, yes. Well, what this guy? I mean, if you look at right, okay, if you're in the plane, then you have to be of this form. Okay, but you can take the Cartan projections of these guys and you can hit the wall. Okay, or the Jordan projections of these guys. Okay, so one thing to point out is that because of this, right, you know that the conjugacy class of any group element is completely determined by the eigenvalue data. Okay, if you know the three eigenvalues, you know which conjugacy class it has to be in. okay? And also, there are some restrictions on what your eigenvalues can be, okay? For example, your eigenvalues cannot have opposite signs, right? So there's some restriction on that as well. Okay, and also here, furthermore, okay, if gamma is hyperbolic, is quasi-hyperbolic, or parabolic, then it has to be peripheral. Okay, so the only time you can have a quasi-hyperbolic element or parabolic element show up is when you correspond to a puncture, right? You're going around a puncture. Okay, so in particular, if your surface is closed, then the only things that can show up are the hyperbolic ones. Okay? And the way that you can prove this is basically you just look at all the possible conjugacy classes in PGL3R and you analyze the dynamics of iterating that group action, okay? And you can see that if you want to preserve a properly convex domain, these are the only three possibilities that can show up. Okay, so let me just show you what the dynamics of these three guys look like. Okay, so in this case, if you're in this case, right, you're going to have three fixed points, right, corresponding to the three eigenlines for these three eigenvalues, right, inside of RP2. And because of that, you're going to preserve the three lines through these 3 points. Okay, so these are lines stabilized by the group element as well. And then, okay, so let's say that this guy corresponds to the eigenvalue lambda 1, this guy corresponds to lambda 2, and this guy corresponds to lambda 3. Okay? Then this guy corresponds to the largest eigenvalue, right? So this is an attracting fixed point. So you have everything just getting sucked into here when you hit this picture by the group element. Okay, and this guy, lambda 3, is the repelling fixed point. So everything's getting pushed away. Okay, and this point here, this is the saddle fixed point. Okay, so in some directions it's getting pushed in some directions it's getting pushed away. Okay, and then if you pick an arbitrary point, a generic point in this picture, so it avoids the line. Okay, and you keep iterating the group element on this guy, on this point, right? What you're going to see is an orbit that is tangential to these two lines. Okay, and it's going this way, going towards the attractor, away from the repeller. Okay. So this is what the action of a hyperbolic element look like in RP2. Okay, so what about the quasi-hyperbolic guys? Well, here you have two cases depending on whether lambda 1 is bigger than lambda 2 or lambda 1 is less than lambda 2, but they're very similar. Okay, so I'm just going to draw one of them. So in this case, you're going to have, this group element is going to have two fixed points in RP2 corresponding to this eigenline and this eigenline. Okay, so you have two fixed points corresponding to lambda 1 and lambda 2. Then since the lambda 1 and lambda 2 are fixed, the line through lambda 1 and lambda 2 is also fixed, right? That corresponds to the span of the first and third vector. Okay, but the eigenspace for lambda 1 is also preserved by the group, okay? So that is what this line is, the eigenspace for lambda 1, okay? And then if you look at the dynamics here, so I'm assuming that lambda 1 is bigger than lambda 2. Then along this line, you're attracting towards lambda 1 and you're repelling away from lambda 2, okay? But along this line here, right, this is not an attracting fixed point anymore. Okay, so it acts as if they're like a parabolic element. So it goes like this. Okay? And so if you pick a generic point inside of RP2 and you keep hitting it by this group element, what you're going to see is an orbit that is tangential to this line here, right, and tangential to this line here. Okay? And basically this kind of picture forces you to not be, the only way this kind of things can show up is if you're peripheral. Okay? Because your domain, you cannot have a domain on both sides, right? You violate convexity here. Okay? And then if lambda 1 is less than lambda, you just reverse the same picture, you just need to reverse some arrows. Okay, so in this case, the arrow goes this way. Okay? And the final type is parabolic. In this case, you only have one fixed point corresponding to the first vector. Okay? And then you have a fixed line corresponding to the span of the first two vectors. Okay, and this is the only fixed data of this element. And then the dynamics is getting something like this. And you pick a generic point in the space, okay, the orbit, right, looks something like this. Yep. Okay? So these are the only kind of things that can show up as holonomies of a convex projective structure. No. Yeah, I'm just taking any convex projective structure. But that's a good point, right? There's a strong relationship between what can possibly show up in the holonomy and the finiteness of the volume. Okay? Yeah, so maybe I should state that as a proposition now. Okay, this is also due to Maki. Okay, so a finite type convex RP2 surface with negative Euler characteristic, right, has finite volume if and only if every peripheral element in gamma is parabolic. Okay? Basically what happens is that when you have a n that is hyperbolic or quasi-hyperbolic, you can find a sequence of points going towards the n, okay? And a sequence of numbers going to infinity, so that for every point as you go out, you can put a bigger and bigger embedded disk inside of the surface. Okay? And that forces your volume to be infinite. Okay? And then you show that in the case of when you're parabolic, you can find, if you take you can find an upper bound for the volume of the n, which is independent of what the rest of the surface looks like. Okay? And so when all your n's are parabolic, the volume is just the volume of a compacting plus the volume of finitely many n's. Okay? And so therefore that will tell you that it's finite volume. Okay? Okay, so that's all I want to talk about convex. I want to say about convex RP2 surfaces for now. Right, next, we're going to talk about convex RP2 structures on S. Okay, so recall again that S is a negative is a orientable finite type with negative Euler characteristic. S. Yeah, you get funnels, but you get some kind of funnel, but the funnel is different from the funnel that you get this way. So if you take a convex co-compact hyperbolic structure and you view it as a convex projective structure via the Klein model, right? The only kind of ends that show up is this kind. If you take a finite volume convex projective hyperbolic structure and you view it as a convex projective structure, then all you have is this kind. So this kind it doesn't show up as if you just look at the Klein models. Okay. Any other questions? Okay. So what is a convex RP2 structure on a surface? Okay, definition: a convex RP2 structure on S, right, is an equivalence class of a pair. Let me give the equivalence class a name. F sigma, right? Yes. Yes, this quotient volume. That's right. Okay. Okay, so a convex RP2 structure on S is an equivalence class F sigma, where sigma is a convex RP2 surface. Right, and F from S to sigma is a homeomorphism. Okay, and what is the equivalence relation here? So I say that one such pair, F1 sigma 1, is equivalent to another pair, F2 sigma 2, if when you look at F1 composed with F2 inverse, from sigma 2 to sigma 1, okay, this guy here is isotopic to a projective isomorphism. Okay, and you can think of this a convex RP2 structure as a set of instructions to tell you how to equip your naked topological surface with some convex RP2 clothing, okay? You basically pull back the convex RP2 structure from sigma onto S, okay? And this equivalence relation is saying that, well, if I have two different ways of pulling back convex RP2 structures onto my surface, then I can kind of wriggle from one to the other, right? Then they are basically the same way as of putting on this structure. Okay, it's just like, you know, when I wear clothing, right? If I, with this way of wearing it, I kind of wriggle my clothing a little bit, that's basically the same way of wearing my clothing. Okay, an essentially different one is if I try to wear, you know, my arms through my collar and my waist through my sleeve, then that would be a completely different way of putting on this convex projective clothing. Okay, so that's how you should think of this definition, right? This is saying I'm only consider pullbacks up to wriggling. Okay, those are the same thing. Okay. Okay, and then another piece of notation. I'm going to let CS, okay, denote the deformation space of a convex RP2 structures on S. Okay, and by the Klein model, inside of here, right, you have the space, the deformation space of hyperbolic structures on S. Okay, so when S is closed, you have a copy of Teichmüller space sitting inside of CS. Okay, but inside of here, you also have the finite volume convex projective structures on S. Okay, and those I'm going to call CS or finite FV. Okay, so basically, the convex projective structures where the holonomy about all the ends are parabolic. Okay? Okay. So the next thing I would like to explain to you is how to topologize this space. Okay, so this deformation space of convex RP2 structures, right, is an example of an XG structure that Stefano told us about last Friday. Okay, and so for any such structure, it comes together with a holonomy representation and a developing map. Okay, but these guys, the holonomy representation and the developing map in this case can be described much more easily than the construction that Stefano gave us. But this is something that's special to these convex projective structures. Okay, so you start with mu, which is equals to F sigma inside of CS, so a convex projective structure on S. Then from here, you can get two pieces of data. The first one is called the developing map. Right, the same developing map as the one that Stefano told us about. Okay, so I'm going to denote this by D, or sometimes I'll denote it by D mu if I want to record the convex projective structure it comes from. Okay, and this is basically just the lift of F to its universal cover. Okay, so this goes from S tilde to omega. So here sigma is omega quotient out by gamma. Okay, which is a properly convex domain inside of RP2. Okay, so this is the developing map. And then the holonomy representation rho, which I also sometimes denote as rho mu, right, is the push forward of F. Okay, so this goes from the fundamental group of S to gamma, right? The fundamental group of sigma, okay, which is a subgroup of PGL3R. Okay, and it's not hard to see that the fact D is row equivariant. Okay, and so the pair D row here is called a developing pair. For mu. Okay? So whenever I'm given a convex projective structure, I can produce a developing pair. Okay, but note that to produce this developing pair is not unique because I made a choice here. Right? My choice is I chose a representative in this representative pair in this class, right? In this equivalence class of pairs. Okay, to do this. Okay, so the question now is, well, given any map D to RP2 and any representation rho from gamma from the fundamental group of S to PGL3R, when is that the developing pair of a convex projective structure? And also, given two developing pairs, can I tell when are they the developing pairs for the same convex projective structure? Okay, so that's what we're going to talk about next. I'm just going to state this as two facts. Okay, these are quite, I mean, the proof is just basically comes from understanding the definition properly. Okay, so the fact. So if D, let's start with rho. If rho from the fundamental group of S to PGL3R is discrete and faithful, okay, so that means it's injective with discrete image, okay, and D from the universal cover of S to RP2 is a row equivariant homeomorphism onto a properly convex domain. Okay, then D row is a developing pair for some mu in CS. Okay, and second, D1 row 1 and D2 row 2, right, are developing pairs for the same mu in CS. Okay, if and only if there exists a projective transformation G in PGL3R. Okay, so that row 1 is conjugate to row 2 via G, and the image of D1 is equals to G times the image of D2. Okay? So here I'm using something special about convex projective structures, namely that the developing map is injective. Okay, so for example, for CP1 structures, this is not true, right? You cannot say what the developing map is just from its image. Okay? Okay, so these two facts tells you how to topologize this deformation space. Okay, so CS can be topologized right, by the compact open topology on the space of homomorphisms from pi1 of S to PGR3R, right? And the topology on induced by the Hausdorff distance on the set of properly convex domains in RP2, okay, with respect to any Riemannian metric. On RP2. Okay? So, okay, more explicitly, in other words, this says that if you have a sequence of convex projective structures in CS, right, converging to a limiting convex projective structure, mu infinity, this is true with respect to this topology, if and only if if and only if there exists developing pairs di rho I and d infinity rho infinity for mu I and mu infinity. Okay, so that rho I converges to rho infinity in the topology here, and di of S tilde, this properly convex domain, converges to d infinity of S tilde, right, in terms of the topology here. Okay? So this is how I topologize the space. And then from this topology, right, so note that if you take the holonomy map, right, so this is a map from this deformation space to the space of homomorphisms from the fundamental group of S to PGR3R. Consider up to conjugation by PGR3R. Okay, I'm going to denote this by X3 of S for short. Okay, this guy here. So, okay, what is this map? Well, you take any mu and you send it to the conjugacy class of its holonomy representation. Okay, so this fact here tells you that all the holonomies are conjugate, right? Okay, so you do this, and this guy here is a continuous map. Okay. Questions? Okay, so this is what the topology on this deformation space looks like. Okay, so in particular, so this tells you how to. So this gives you a topology on the finite volume guys as well. Okay, just by taking the subspace topology. Okay. So next, I would like to describe the symplectic structure on this deformation space. Sorry, say that again. Right. If you don't have the holonomy. Right. So, for example, if you're Fuchsian, right? I mean, if your convex projective structure is is a hyperbolic structure, then this is always the same, right? Okay? Okay. Okay, so, right, so now the symplectic structure. What section is this now? 1.5. Okay, so here, this is, the way I'm going to describe it is largely following the work of Goldman, who described this in the case when S is compact. And then he had a student, Hong Chang Kim, who generalized what he did to the case when S is of finite type. Okay? So what to do here? Okay, the first thing, okay, so really the symplectic structure that Goldman defined is on X3S. Okay? So, let me see how to say it exactly. Okay, so maybe the first thing to say is that if you look at the image of the finite volume guys under the holonomy map, okay, this guy here is naturally a real analytic manifold. Okay, so why is this? So it turns out that, okay, if you look at this space X3S that we defined, right? We took, there's a topology on this space, the compact open one, and then we took the quotient topology here, okay? Now the problem with this is that this topology is not even Hausdorff, it's not good. Okay, so we don't like the topology in this space. But usually if you have a non-Hausdorff space and you want to make it nice, what you do, you take its Hausdorffification. Okay, so you can take a further quotient of this guy to get X3 Hausdorff of S. Okay, and basically what you do is you just take the points that you cannot tell apart using open sets, you just identify them. Okay? Then this part is something that I don't really understand. Okay, there's this whole GIT theory that tells you that this guy here is a real algebraic variety. And then you want to take a quotient by a real algebraic group, okay? So there's a way you can do it in an algebraic way, okay, to make this guy a real algebraic set, and that set is homeomorphic to this guy. Okay, yes. No, that's not correct. That's true for... It's not going to be algebraic. Okay, but it doesn't matter. The only thing I need is the real analytic structure. Okay, so maybe you don't have the algebraic part, all you have is the real analytic structure, that's good enough. Okay, but the point here is that if you look at the image of this guy, okay, if you look at the image of this guy, okay, the representations in here are all irreducible. Okay, and so Goldman tells you that they avoid all the singular points, right? Of this space, okay? So on the complement of the singular points, you are a real algebraic variety. You are a real algebraic manifold. Okay, so that's how you get the structure here. Okay? So this is the first thing. And the second thing is that if you look at the tangent space for any point in here, right? Okay, if you look at the tangent space in here, this guy here is canonically isomorphic, okay, to the first cohomology of your surface. Relative is boundary. So when I say boundary here, I mean you just take column neighborhoods of the ends, okay, with values in the Lie algebra G twisted by arrow. So G here is the Lie algebra of PGL3R. Okay, and so why is that? Well, I think the easiest way to think of this is using group cohomology. Okay, so a co-cycle here is just a map from the fundamental group of S, right, into this Lie algebra G. Okay, so given a tangent vector in here, how do I get such a a cochain, right? A tangent vector here. How do I get a cochain? Well, basically, you take a path of representations, right? You deform you start with your representation row and you deform it in a smooth path. And you want to look at the tangent vector to that path, okay? So that smooth deformation, right? If you evaluate the family of representations on a group element, that gives you a path inside of the group that's smooth, and then you can take the derivative of that path, which is an element in the Lie algebra. Okay, so that procedure assigns an element in your Lie algebra. Okay, now but then this maps that we get from this procedure, right, are not just arbitrary maps. Okay, because they come from homomorphisms. Okay, so when you differentiate the homomorphism condition, that gives you the cocycle condition here. Okay, and also here we're considering things up to conjugation. So if you linearize the conjugation up to conjugation condition, that gives you the co-boundary condition here. Okay, so this is what this identification is. Okay, and the third thing is you can now define a skew-symmetric bilinear pairing on this space. Okay, so you take S, boundary of S, G at rho. Right. So here my around the puncture it all has to be 0. Has to be 0. Okay. Right. So I guess that's what this thing means. Right. And the way you think about it is because when I talk about my deformation like what I did just now, I'm always keeping the conjugacy class of the peripheral elements fixed. Okay. So the derivative of those guys are always 0. Okay. And that's why you get a cohomology class rel boundary here. Okay. So now you have 2 copies of this, right? And you can assign to this a second cohomology class, again, rel boundary, right, with coefficients in R. Okay, and so how do you do this? Well, given 2 first cohomology class, there's a natural way you can get a second cohomology class, right, which is taking the product. Okay, so you take the cup product. Okay, but if you just take the cup product, you're going to get a second cohomology class with coefficients in G at rho tensor G at rho. Okay, but I want real coefficients, so I need to find some way to pair the coefficients here in an at-row equivariant way. Okay, and the way you do it, well, there are many ways you can do it, but one way you can do it is to take the killing form here. Okay, so PGL3R I mean, the Lie algebra of PGL3R is semisimple. So this killing form is non-degenerate bilinear. Okay, so B here is the killing form. Okay, so this cup product is skew symmetric. This B here is symmetric. Okay, so this will give you a non-degenerate skew symmetric pairing. Okay, and then but I want a symplectic form, right? I want a 2 form, so I want to identify this with R. Okay, and the way you do it is you take the cup product with the fundamental class of S. And here the fundamental class of S, I'm thinking of it as inside of the second homology of your surface, rel boundary. Okay. Okay, and I guess the hard part of this whole thing is that this guy omega here. Okay, first it's non-degenerate skew symmetric. Non-degenerate skew symmetric. And I guess the main point is that is this guy enclosed as a 2 form on the image of this guy. Okay, and this part is the only non-trivial thing in this. Everything else is just follows from the definition. Okay. So in particular, this gives you a symplectic structure. On Hall of CS finite volume. Okay? And then the final thing is, okay, so here's something that also was proven by Marquis. maybe I should, but this is, it basically follows quite easily, or with some, you need to analyze some special cases from the theorem where he classifies the ends of convex RP2 structures on surfaces, okay? So the fact here is that the map, the holonomy map, when you restrict it to the finite volume convex RP2 surfaces, to the space of homomorphisms from gamma, from pi1f to x3s. Yes. Instead of the finite volume. Right. The problem is you don't have this identification. Right? Because here I need to make sure that as I deform my representation, the group elements corresponding to the peripheral, and the peripheral group elements, their conjugacy classes doesn't change. Because if the conjugacy classes are changing, that means you have something that's non-zero in the peripheral element. Right? Okay? Right, so maybe I should point out also that if you remove the finite volume guy, right, this Hall of CS, this guy here is supposed to have, it's not a symplectic manifold, but it's supposed to have a natural Poisson structure as well. Okay, and maybe Francois might talk about that in his mini course, maybe. Okay? Okay, so the fact here is that this guy here is a homeo onto his image. Okay, maybe I should call this a theorem, because I guess the continuity of the inverse is not completely obvious. Okay, so but because of this, right, you can think of this guy as really sitting inside of X3S. Okay, and so this procedure defines for you a symplectic structure on this space. Okay. And a real analytic structure on CS finite volume. Okay, so these are the structures that we're going to try to study next time on CS of finite volume. Okay, so I have 2 more minutes. Okay, so maybe I can introduce one, or at least sort of introduce one important tool that we can use to describe these symplectic structures and this real analytic structure. Okay, and this is the flag map that you can associate to a convex projective structure on the surface. Okay, so maybe I'll continue. I'll just start saying a little bit, and when time is up, I'll just continue next time. Okay, so what are the flag maps? So the first thing you do is choose a convex co-compact hyperbolic structure on S. Okay, so this means that in terms of the hyperbolic metric, your surface looks like this. Okay, you might have some topology. Okay, but the ends is they are flared. Okay, they're not cusps. Okay, so this allows you to identify the universal cover of S with the Poincare disk. Okay. So I should say that really this whole story, you can describe it without choosing a convex co-compact hyperbolic structure, but doing this is just maybe shorter and easier to explain, but nothing that I'm going to say depends on this choice. Okay? Okay, and then, okay, now if you take any non-identity element in gamma, okay, this guy is going to have, gamma has an attractor and repeller. Right, which I'm going to denote by gamma minus and gamma plus inside of the boundary of D. Okay, yes, this north-south dynamics for every non-identity element. Okay, and so I'm going to define U, right, to be the set of fixed points of the elements in, so this guy lies inside the boundary of D, of the elements in gamma, they are not the identity. Okay? So 5 seconds. So for any convex projective structure on S, okay, you can get a holonomy representation rho from the fundamental group of S to PGL3R. Okay, and using this next time, we're going to produce for you a map C from this set U into the space of flags in R3. Okay, and this will be the main tool we'll use to describe these symplectic and invariant structures. Okay, so I'll stop here. Thanks. Yes. Yeah, this guy is a one real dimensional homology group, and you just look at the generator. Right.
So, any other questions? That's all. So let's thank Tengren again.